Okay, this is 2018, number 2. And so you can see the setup that we have. We've got a cart of 9.5 moving to the right at 3. Has a force sensor attached. It hits a cart of mass 1.05 with a spring attached. The spring has a spring constant of 130 newtons per meter. It's at rest. The modeling of the force experienced over time. And that force can be given by 3200 t squared minus 500 t. Okay, so this is our force equation. In A, they say using integral calculus, calculate the total impulse. Well, impulse is the integral of f of t dt. And so that's what we're going to do. We're going to integrate our function, 3200 t squared minus 500 t dt. And we're going to evaluate it from, so I look at my graph and I say, well, what do I do? I start at 0 and I end at 0.16. So we're going to go from 0 to 0.16. And so we get 3200 t cubed over 3 minus 500 t squared evaluated from 0 to 0.16. And so I plug my values. 3200 times 0.16 cubed over 3 minus 500, oh, this is over 2, I forgot that part, times 0.16 squared over 2. And then I would subtract the 0, so minus the 0, but when I put in 0, I get 0 and 0. So I'm not going to do that. So I get 2.03 Newton seconds, and it's negative. So that's what the force that cart, or excuse me, the impulse that cart 1 experiences. On B, it says, okay, so calculate the speed of the cart after the collision. Well, impulse is change in momentum. So if that cart experiences negative 2.03 Newton seconds, that's going to equal its mass, which is 0.5, times its V final, minus its V naught, which is 3. Now, where do I get that from? Because change in momentum is mass times change in velocity. And that's what this is, V final minus V naught. So we divide both sides by a half. I get negative 4.06 is equal to V final minus 3. I add 3 to both sides, and I get negative 1.06 is equal to V final. So let's clean that up. 1.06 meters per second is equal to V final, because you know unit points, they matter. And that was I. On I, it says, which direction is it going? Well, that said negative. So since that's negative, it's going left, because I said 3 was positive. Okay, part C. It says calculate the speed of cart 2 after the collision. Well, if cart 1 gets this impulse, cart 2 gets the same impulse, but it gets it in the other direction. So that's going to equal 1.05 times his V final minus his V initial, which was 0. So we divide by 1.05. And so V final is approximately 2. 2.03 divided by 1.05, 1.93 meters per second. So there's the final velocity of that one. That was CI. I says show that this collision is elastic. Well, elastic means K naught is equal to K final. So I'm going to do a kinetic energy in the beginning, which would be a half times that first mass times its velocity squared. The other one doesn't have a kinetic energy. It would be 1/2 times 1.05 times 0 squared, so I'm not going to put it on the left side. On the right side, I've got a half times 0.5 times its final velocity, which is 1.06 squared. Now I know it's negative, but it's going to be squared, so it's okay. Plus a half times 1.05 times 1.93 squared. So let's see what we get. So we get 0.5 times 0.5 times 9. So this side we get 2.25. And over here we get 0.5 times 0.5 times 1.06 squared plus 0.5 times 1.05 times 1.93 squared. And what do you know? I get 2.24. I realize this is not exactly that, but remember this and this are rounded numbers. So that rounding costs me that 1 digit over here. So that's proof that they're relatively. I mean, that is conservation. It's just these roundings that make it look like it's not. Or actually not perfect. It's really, really good. All right, on D. It says calculate the speed of the center mass of the two-cart spring system. Well, velocity of the center mass is just m1 v1 plus m2 v2, all divided by m1 plus m2. It's done just like position of center mass. It's each mass times its velocity added together and then divided by the total mass. So vcom is going to be m1 times its velocity. Now, I can do it before or after. I'm going to do it before because this is 0.5 times 3. This is going to be 1.05 times 0 all over 0.5 plus 1.05. And so when I do that, I get 1.5 divided by 1.55. My calculator said that is 0.97 meters per second. Now, just to show you that it does work, if I do it after, this is before. If I do it after, momentum's got to be conserved. So we do it after, we've got 0.5 moving at negative 1.06, and I've got 1.05 moving at 1.93 divided by 0.5 plus 1.05. You do the math on that. Holy cow, I get 0.97. So it doesn't matter which way you go about that, you can do it either way. All right, and then finally 2, it says calculate the maximum elastic potential stored in the spring. This spring. Okay, so I say, well, elastic potential energy, I know how to do that. It's 1/2 kx squared, right? Okay, so that's going to be a half times that k of 130 newtons per meter times x squared. And you go and you read this and you go, I don't have x. So what can I do? Well, I have a graph, so I can estimate from the graph if I want to, or I could use my function and take the derivative and set it equal to 0 to find my max of the function. So you can do that. I mean, that's also allowable. So when I get to that, I could, but I could look at this and say, well, that looks to me like it peaks at about like 21. So I'm going to say the force of the spring, which is equal to kx. I know it's equal to negative. It's okay. So the force of the spring is like negative 21 newtons, and that's 130. So I could find x, because at a maximum force is when I'm at my maximum compression. So I divide by negative 130. That's 130, not 1.3. So that goes away. That goes away. 21 divided by 130 is 0.16. So that's my maximum compression. So I put that in to get my maximum energy. So 0.5 times 130 times 0.16 squared gives me 1.67 joules. And that's my maximum energy.